The problem we're going to solve is a static equilibrium problem involving a ladder leaning against a wall. We're told it's a 10 kilogram ladder, 5 meters long, frictionless wall, and that as the end of the ladder gets pulled out, so that the angle here becomes smaller and smaller, when the point comes that this angle against the floor is 50 degrees, the bottom of the ladder starts to slip out. So the question is, what is the coefficient of static friction between the ladder and the floor? So like our other static equilibrium problems, you need to draw a picture of the object and put forces on it. So let's do that. I'm just going to dot in where it's touching other surfaces, the floor and the wall. Where that happens, there's going to be a normal force. So we can draw normal force here, normal force there. You also have to consider the weight of the ladder. We assume a uniform ladder, so we put that force vector right in the middle. And then finally, friction. No friction with the wall, but with the floor, the bottom of the ladder is trying to slip off to the left the way we've drawn it. So to resist that, we have a force of static friction pointing to the right. So let's get all those forces labeled. Force of static friction, normal force on the floor, we can call that normal force 1. With the wall, we have normal force 2. And here we have the force of gravity on the ladder, which is a 10 kilogram ladder. So let's just fill that in, 98.1 newtons. Like other static equilibrium problems, we know that all the forces have to balance and all the torques have to balance. So let's deal with the forces first. All the forces sum up to 0. Let's start with the x components. And we've got two forces with x components. We've got the force of static friction to the right, and we've got the normal force from the wall going to the left. So the force of static friction and the normal force, Fn2, are going to be equal to each other. We don't know what either one of those forces is, so we're going to have to come back to that. Also, our y components have to sum to 0. So we've got the normal force up, the force of gravity down, so that normal force has to equal the force of gravity of the ladder, which is 98.1 newtons. Okay, now let's look at the torques. For the point where we're going to choose as our pivot point, let's pick the one that two forces go through, and then we don't have to involve those ones in our torque calculation. So we're going to pivot around the red dot, first our counterclockwise torque. Okay, so we're going to use RF sine theta. And I think you can see the Z pattern there. So that theta is going to be 50 degrees. Okay. The length of the ladder is 5 meters. So for that torque, which is all the way at the other end of the ladder, 5 meters times Fn2 sine 50 degrees. All right, then for our clockwise torque, which is negative from the weight of the ladder, that is halfway up the ladder, so 2.5 meters times 98.1 newtons. And this angle, well, that's 50 degrees here, and you can picture that right angled triangle. This one has to be 40 degrees. And if you solve that, then you will see that the only unknown in that equation, Fn2, is 41.2 newtons. So we now know Fn1 and Fn2. And if we go back to where we were dealing with the x components of the forces, if we substitute Fn2 in that statement, then we'll see that the static friction force is also 41.2 newtons. Okay, we have dealt with all the forces and torques without even thinking about the slipping condition. Why does it matter that the ladder is about to slip? Well, the ladder slips when the static friction force reaches its maximum value. Just like when you did the experiment with the brick to find the coefficient of static friction. You need to know the maximum value of static friction before you can calculate mu. So if you're ever solving a problem with slipping, the force of static friction is equal to the maximum value it can have, which is equal to mu s times the normal force, in this case the normal force with the floor, and you are in static equilibrium. So having solved then for Fs, we take it to be Fs max, and we can then say that mu s is equal to the maximum force of static friction over the normal force, and that is normal force 1, the value with the floor, 41.2 newtons divided by 98.1 newtons, which gives you 0.420, and you can write your concluding statement. Therefore, if the ladder slips at 50 degrees, the coefficient of static friction must be 0.420. And it is solved. Now, extensions to this that I would like you to try. First, does the coefficient of static friction in this case depend on the mass of the ladder? Second, and this is a more complicated question to solve, take the mass of the ladder equal to 10 kilograms. Again, you can give it a mass. Same coefficient of static friction. Now there's a worker with a mass of 60 kilograms. Two-thirds of the way up the ladder. At what angle does the ladder slip? Let me know if you get 54.0 degrees for that. Good luck!